Hi, Dr. P here, and in this lecture video, we're going to go ahead and talk about the percent composition and determining formulas of compounds. So yes, we will of course involve moles, like this guy, but we'll use them when we are doing some calculations. So let's look at composition of compounds. There are two ways to really look at the composition of a chemical compound. One is the molecular formula, and this is the relative number of atoms per molecule or formula unit. What's a formula unit? Well, it's when we break things down so that we're looking at the lowest whole numbers, relative numbers of atoms in a small portion. Because not all compounds form individual molecules. So something like sucrose, table sugar, does have a formula of C12H22O11, sorry, C12H22O11. But something like table salt, sodium chloride, just has a formula of NaCl. Now you're never going to actually see an NaCl molecule, but rather you'll have a crystal of sodium chloride, a crystal of table salt, in which the ratio of sodium atoms to chlorine atoms, is 1:1. And that's because typically when we talk about molecules, we're talking about covalent compounds. And when we talk about formula units, we're talking about ionic compounds. So for example, we could have water, which is H2O, so 2 hydrogens, 1 oxygen per water molecule, or something like NaCl, sodium chloride, where we have 1 sodium and 1 chlorine per formula unit. Now because these are ionic, it's actually a sodium ion and a chloride ion, which of course you've seen from nomenclature. We can also look at a mass percentage. And mass percent, instead of being relative numbers of atoms, it's the relative masses of atoms. Oops, I should say elements. And so an example would be water is 11.19% hydrogen and 0.81% oxygen. Now, we can also determine the formula of a compound. Given its mass percent. So really we can go back and forth between a molecular formula and a mass percent. So experimentally speaking, what would happen is you would obtain the mass percent of different elements somehow. This could be by stoichiometry, for example. Or let me just put that in parentheses as by stoichiometry. And then what we want to do is convert the mass percentage to a mole percentage. And this is also known as a mole fraction. Now, once you've done that, you can go ahead and get whole number ratios of atoms in a compound. And divide by the smallest of the mole values. And multiply then by to get whole numbers. And this will give the empirical formula. Empirical standing for experiment, or meaning experimental. And then we could use the molar mass, if it is known, to get the molecular formula. Now, if you don't have a molar mass, or let's say you have something that is ionic, then your empirical formula is just your formula unit. So your empirical formula is the formula. Okay, so let's go ahead and look at an example of this. So let's say we had glucose, and glucose is 40% carbon, 40.00% carbon, 6.71% hydrogen, and 53.29% oxygen. What is the molecular formula of glucose? Now, I haven't told you the molar mass, so I'm going to need to do that. So what is the molecular formula of glucose if the molar mass is 180.16 grams per mole? Okay, so okay, seriously, is every time I say mole, that guy going to show up? I don't know. Let's continue. So what would we do? Well, we would go ahead and take 40%, so 0.4000 grams of carbon. We'll call this moles of carbon. And we'll multiply by 1 over the molar mass. So we'll divide by the molar mass. So that's 12.01 grams of carbon per mole of carbon. And we'll see what that gives us. And then we can set that up for moles of hydrogen equals 0.0671 grams of hydrogen. So I'm just converting my percentage to grams. So we have 0.4 grams of carbon per gram of glucose. So each mole of hydrogen is 1.008 grams of hydrogen. My grams of hydrogen will cancel. And then my moles of oxygen are going to be 0.532 5.29 grams oxygen, 16.00 grams of oxygen per mole of oxygen. We'll cancel those. Of course, I forgot my computer, but I do have my calculator, but I do have my phone. So we can go ahead and take a look here. And we can see that if I have 0.4000 divided by 12.01, I get 0.03331 moles of carbon. And then if I've got 0.0671 grams of hydrogen, divide that by 1.008, I get 0.06657 moles of hydrogen. And then if I have 0.5329 and divide that by 16.00, I get 0.03331 moles of oxygen. Now I can do a couple of different things here. So right now I can divide through by my lowest common denominator here. So I could divide by 0.03331, 0.03331, 0.03331. So I have 1 mole of carbon, 1 mole of oxygen, and this guy is actually going to be awfully close to 2. Look at my phone here, there we go. 0.06657 divided by 0.03331 equals 1.998. 1.998 equals 2 moles hydrogen. It is close enough that we can round. So the empirical formula is CH2O. That's our empirical formula. Now, to get our molecular formula, we have to figure out what our formula or our empirical formula mass here is. So our mass equals 12.01 plus 2 times 1.008 equals that, plus 16.00 equals, whoops, it was 30.03 grams. I hit that an extra time and added an extra 16, but 30.03 grams. So now our molecular formula, or rather our number of formula units in one molecule equals 180.16 grams glucose per mole. We'll divide that by 30.03 grams, and we end up with a number that's approximately 6. And I can go ahead and actually do that calculation. 180.16 divided by 30.03 equals 5.999. 5.999 equals 6. So our molecular formula is 6 formula units. So it'll be C6H12O6. Okay, so this involves an intermediate step. Now you don't have to do it this way. You could, if you want to, instead set it up to do it all at once. So let's take a look at what that would look like. So if we want moles of carbon, we have 0.4000 grams of carbon. And that's per, sorry, there should be per 1 gram of glucose. And then we'll multiply that by 180.16 grams of glucose per mole of glucose. So now our grams of glucose will cancel, and we will get grams of carbon per mole of glucose. And then we multiply by 1 mole of carbon per 12.01 grams of carbon. And again, you want to get used to writing things out like this and just doing multiplications. And if you need to do a division, flip your units over. That way, if you're not sure if you should be multiplying or dividing, you can take a look at your units and say, all right, I need to cancel grams of carbon, so I better have grams of carbon in the denominator here. And indeed we do. So let's go ahead and let's do this calculation here. 0.4 times 180.16 divided by 12.01 equals 6.000 equals 6. Okay, and I'll just say etc. And you can do that for hydrogen and oxygen. Same calculation. So it's essentially you're doing this initial calculation but multiplying through by the molar mass to get your actual number of moles. So this is 6 moles of carbon. I should probably have my units in here per mole of glucose. And so you can do that for any sample that you have where you know the mass percent of different elements, and you also know the formula, not the formula, the molar mass. Now, if you don't know the molar mass, then you have to start making some guesses. So, if we didn't know the molar mass, we'd know this is our empirical formula. And so our possible molecular formulas could be CH2O, C2H4O, 2, C3H6O2, C4H8O, sorry, that should be O3, O4, C5H10O5, C6H12O6, C7H14O7, etc., etc. So we'd have to somehow be able to distinguish these, and part of that could be the chemical structure. But usually there are ways to, you can figure out from stoichiometry how many grams of something, let's say, burns, how many grams of this burns with a certain amount of oxygen, for example. And you can determine molar masses that way. All right. So that is how to determine the molecular formula given mass percents. And in the next lecture, we'll go ahead and start looking at chemical equations. But until then, stay safe out there. Bye now.